So this was question number one, and this is where things started to this is where things started to go bad for some people. All right. In question number one, it says in the impulse equation. Hold on, I'm sorry, you guys. All of a sudden, that's not working. All right. Um, so I'm sorry. In the impulse equation, force and time are. Now, here's the impulse equation. Impulse is equal to force times time. Okay. Here, let's see. Is this going to work again for me now? No, it's still not working. I'm sorry. So impulse is equal to force times time. And then we know that impulse is also equal to m delta v. So force times time equals mass times change in velocity. Okay. Now we said that there are two different ways to think about this impulse equation. One way is in a crash. So if I'm involved in a crash, my car hits a tree, right? Squirrel runs out in front of me. I don't want to hit the squirrel, so I accidentally hit this tree. In this equation, impulse is fixed because the mass of my car is what it is. The change in velocity, it's always going to be the same. It'll be whatever my starting speed was down to zero. All right. So when the impulse is fixed, when this doesn't change, right, force and time are inversely proportional. If the stopping time goes up, the force will go down. If the stopping time goes down, the force goes up. All right, so in that situation, they are inversely related. Lots of people put that because that's what they were thinking about. But, so that would have been the second best answer. But the best answer is there's not enough information here. Because if I was the one applying the force, let's say that I was a hockey player hitting a slap shot, right? So I have my stick, I'm putting my stick on the puck. In that case, force and time are not related to each other. Okay, you apply the biggest force you can. You keep your stick on the puck for as long as you can. And in that case, these two things don't have any relationship. But in a crash, they do. In a crash, they are inversely related. So the best answer here, you guys, is not enough information. So that was tough. And I can totally understand why lots of people picked this answer. All right. That would have been right if I said in a crash. Okay. So that was number one. Number two, the front ends of most cars are designed to crumple up like an accordion. So the main reason for this safety feature is what? Well, let's go back to our impulse equation that we just had. All right. Impulse is equal to force times the time, which means that force times time is equal to mass times change in velocity. Okay, so now if I'm in a crash, this is a crash. So if I'm in a crash, what that means is that I want to the mass and the change in velocity are going to be fixed. So here, this is what we were just talking about. This part of the equation, the impulse, is going to stay the same. So I want the force to be as tiny as possible. I want the people in this car to feel as little force as possible, which means the stopping time has to be as big as possible. So I'm not decreasing the impulse. Lots of people put that on their quizzes. All right. I'm not decreasing the impulse because the mass and the change in velocity, that is going to stay the same. All right. Not helping the failing economy. But if the crumple zone activates, you guys, probably going to have to get a new car. Might help the economy. The real reason I'm doing it is to increase the impact time in order to decrease the impact force. Okay, So either one of those answers, A or B, they're actually both saying the same thing. I don't know why Mr. Hammond and I put those both on there. That was a mistake. Okay, but either A or B would be correct. Because what I really want to do is I want to decrease the impact force by increasing the impact time. All right? These are saying the exact same thing. Does everybody understand that question? Yep. Okay. So now let's go on to the third one. So in this question, I have a bug and it's hitting the windshield on my car while I'm driving down the expressway. Okay. I want to know which has the greater change in velocity. So I'm going to have to try to draw here. So here's my car. It's kind of boxy. All right. And here's the bug. Now you can imagine this bug is just barely kind of moving around here, right? And the car's cruising down the expressway at, say, 55 miles per hour, right? You've been in this situation probably before, where you're driving down, you're doing 55, some country roads you could do 80, right? And you get a bug and it hits your windshield. Is there any significant change in velocity for your car that you could tell? I've never been able to notice, right? I'd never noticed my car slowing down. So which one has the bigger change in velocity? This bug was like just kind of flying, and all of a sudden after it splatters on your windshield, it's going to be going like 55, right? So the greater change in velocity is for the bug. Now, why is that? Remember, according to conservation of momentum, you guys, the total momentum before something happens is going to equal the total momentum after something happens. So this is the original momentum, this is the final momentum, right? So the starting momentum and the ending momentum, they have to be the same for all of the objects. So I would have the mass of my car, I would have the velocity of my car before the collision. Then I would have the mass of the bug and the velocity of the bug before the collision, okay? That's going to have to equal all of the momentums added up afterwards. So that'll have to equal the mass of my car and the new velocity in my car. I'm going to call that velocity prime. That's a notation that they'll use in most college physics books. And I have the mass of the bug times the new velocity of the bug, okay? Now, the momentum change, the total momentum is going to stay the same. Whatever momentum change that this bug goes through, right? Like if the bug loses momentum, then the car gains momentum. If the bug gains momentum, the car will lose momentum. So if the bug was headed straight at the car, you guys, the car will slow down a little bit. But why doesn't it slow down as much as the bug? Because the mass of the car is significantly bigger than the mass of the bug. So the velocity change in the car is going to be small. The velocity change in the car will be much bigger. I don't know if that makes sense to you. Now, if I had asked the question, which one has a bigger change in momentum, what would the answer have been? You guys can type it in. So which undergoes the bigger change in momentum, the car or the bug? What answer would it have been? A, B, C, or D? Type your answer in the chat box. Nobody's going to type? Is there nobody in this meeting? So I know Brian and Angel are here. I don't know about anybody else. But the actual answer, you guys, would be C, right? It's C. The change in momentum would be the same for both. Okay. Now, if we go to the next question, the next question deals with this exact same thing. Okay. So I have the bug and it's hitting the windshield. This question actually goes back, kind of, to our last unit. You can answer it from this unit because remember, impulse equals change of momentum, right? Which is m delta v, and it also equals F times t. Okay, so the impact time of the bug on the car and the impact time of the windshield on the bug, that has to be the same. So this impact time has to be the same. The change in momentums for the two objects, you guys, we just said was the same. So if change in momentum is the same and time is the same, then what has to be true of force? The force acting on the bug and the car has to be the same. So for this one, the answer is C. Now, you could have answered that just because you remember Newton's third law. For every action force, there's an equal and opposite reaction force. So if the action force is the windshield hitting the bug, the reaction force has to be the bug hitting the windshield. Those have to be equal amounts of force. So they have to be the same. The reason that a lot of my students get confused is they say, well, nothing happened to the windshield and the bug splattered. That's just because the bug can withstand less force, not because it got a bigger force. So that's number 4. And then here's number 5. I have a car, it slams into a brick wall. Where does the momentum transfer to? Everybody just put in what you think is the right answer. So I got 2 people. All right. So most of you seem you're either at A or C, right? So I like the fact that you're thinking about the passengers inside the car, you guys. But the answer is actually A. Okay. So if you slam into this brick wall, the momentum of the car and the passengers and all that is going to get transferred into the wall. And the wall will probably break. Or maybe not, if it's super solid. Maybe the car breaks. I don't know. But it's one object crashing into another object. Okay. And now we get to the problems. Like I said, the people who turn their quizzes in, the problems were pretty good. Okay. I might have to turn on my settings. Let's see. So I have a softball player, and her bat makes contact with the ball that's sitting on a tee. Now, if you guys know about how tees work, right? You ever play t-ball? The starting speed is 0 meters per second. Here, I'm sorry, you guys. I have to fix this tablet. This is not going to work for me. Come on. Oop, that's the wrong one. For some reason, this just has to be reset. Okay. All right. So the starting speed of this ball is going to be 0 meters per second. The final velocity, or how fast it flies off the tee, that's what I'm trying to figure out. Okay. Now, if you see that the starting speed is 0, what that means is that the change in velocity is going to equal the final velocity, right? Those will be the same thing. So I could actually just solve for change in velocity. Now, the bat is on the ball for 0.18 seconds, and the player applies a force of 200 newtons. And then the ball has a mass of 0.2 kilograms. So if I look at, I know mass, I know force, I know time, I don't know change in velocity. So the equation I have for that is force times time equals mass times change in velocity. Now you guys, don't get sloppy with showing your work, because some of the people that turned in their quizzes, I could not follow their work and I just saw an answer. If remember, the right answer is only worth 2 points. So if that's all you show, you only get 2 out of 10. All right. Right now I've got 6 out of 10 points though, because I wrote down what I'm looking for, what I know, and then the equation. And then I'm going to stick the variables into this equation. So I have 200 newtons times 0.18 seconds. That's going to equal the mass, which is 0.2, times velocity. Now if I just do the arithmetic here, can someone tell me what 200 times 0.18 is? I know there are a whole bunch of people that got it right. I got 36. So 36 kilogram meters per second, that equals 0.2 kilograms times V. Now I got to get 0.2 by itself. So I'm going to divide both sides by 0.2. On this side, that'll go away. And then over here I have 180 meters per second is going to be the velocity. So if you were able to apply this much force, which is, roughly like 50 pounds of force, for this long on a softball, man, it would be going fast. That's over 360 miles per hour. But you can see why, especially because in softball the pitchers are closer to the batters. The contact time isn't this high. It's significantly lower than that, but the balls can leave the bats at a very, very fast speed. And that's why in softball the pitchers have to wear protective gear, especially a helmet, because it's really dangerous for them to have that ball flying back at them. Okay, so let's do problem number 2. In problem number 2, I have a stationary 3,200 kilogram Buick. So I'm going to draw myself a picture, just easier for me. So I have a Buick. It has a mass of 3,200 kilograms, and it has a velocity of 0, right? Stationary means it's not moving. Now there's a Honda that's coming up behind it, and it's going to rear end it, okay? The Honda has a mass of 1,850 kilograms, and it's got a velocity of 28 meters per second. Now, after they collide, it says that the bumpers lock, so they kind of like mash into one car. They're all mangled together, right? Moving as one. So if their bumpers lock and they're kind of moving as one car, then the new mass of this would be 5,050 kilograms. And then it asks, what is their velocity after their collision? So remember, all of the momentum before the collision has to equal all of the momentum after the collision. So the original momentum has to equal the final momentum. So m times v for the first car plus m times v for the second car has to equal m times v for this combined car. So I would have 1850 times 28 plus 3,200 times 0. That's going to equal 5,050 times my velocity. 3,200 times 0 is 0. Can someone tell me what 1,850 times 28 is? Okay, so it's 51,800. And that's going to equal 50 times v. Now you guys can see 51,800 plus 0, that's just 51,800. And then if I want to get v by itself, I would need to divide both sides by 5,050. So those will cancel out. And I'll be left with velocity equals 10.3? 10.25. And if you guys rounded it to 10.3, that is totally fine. The reason I said 10.3 is I actually remembered seeing that on a bunch of people's papers. Okay. So that was the answer to that question. Now I'd like to do 2 more problems, you guys, before I let you go today, just so you could see like kind of one of every type of problem. So we had an impulse and momentum problem. We had a conservation problem that was a collision. And this is just a basic momentum problem. So let's look at just a basic momentum problem. I have a sprinter, and they explode out of the blocks and accelerate at 3 meters per second for 2.5 seconds. So their acceleration is going to be 3.5 meters per second squared. Oh, I'm sorry, it's not 3.5, it's 3. Okay, 3 meters per second squared, and then the time that they do that for is 2.5 seconds. Now it says that the sprinter has a mass of 54 kilograms. I want to know what is her momentum at the end of that 2.5 seconds. Okay, well, the basic equation for momentum, you guys, is mass times velocity. So I know her mass, but I don't know her velocity. I'm going to have to find it. So I'm going to have to find her final velocity. I have an equation for that. Final velocity is acceleration. Oops. Hold on. Final velocity is original velocity plus acceleration times time. So the final velocity is 0 because she is in the blocks. That's how you start every race, right? You start from a stop. And now I need to add in her acceleration times time. So the final velocity would be 7.5 meters per second. Okay. To find her momentum, I would just have to take the mass, 54 kilograms, times the velocity, 7.5. And so then that momentum would be, can someone punch that in their calculator for me? Okay, well, I got 405. Oh, someone else confirmed it with me. So I got 405 kilogram meters per second. So this, you guys, could show up a question like this on your test, right? Where it's just straight up momentum, P equals mv, but you may at some point have to, use your old speed equations. And then the very last type of problem that I could give you, that would be an explosion problem. So this would be an example of an explosion problem. I have an astronaut and they're in outer space. Okay, so here's my astronaut. They're floating around in outer space. Got a big helmet on, right? Okay, and it says that they have a mass of 64 kilograms. Okay. Now, they have a wrench in their hand. They're out fixing the space station, right? And they think it might be fun. They're going to throw the wrench. The wrench has a mass of 2.3 kilograms. So they throw the wrench in one direction. Now, because we're in outer space, there's no friction, okay? They're in apparent weightlessness. So they don't really feel any forces acting on them. So the mass is 2.3, and then it says that the wrench leaves his hand at 14 meters per second. Now in these collision problems, remember, the total momentum when they were both stopped is going to be 0. The total momentum after he throws that wrench is still going to have to be 0. So the wrench goes in one direction. We'll say that it has positive momentum. The astronaut is going to go in the other direction. So we'll say he has negative momentum. And these two momentums, when we add them together, it has to equal 0. What that means is that the mv for the wrench has to be the mv for the astronaut. So these two things have to equal each other. M times v for the astronaut has to equal m times v for the wrench, right? And how we described it before was the mass of the gun and the velocity of the gun has to be the mass of the bullet times the velocity of the bullet. We'll call the astronaut the gun and the wrench the bullet in this case. So this would be 64 kilograms times the velocity is going to equal 2.3 kilograms times 14 meters per second. So I have 64 times v. Can someone tell me what 2.3 times 14 is? 28. I get it to be like 32.2. That's just in my head. Let me do it. Oh, yep, I was right. 32.2. Okay, and then I have to get v by itself, so I got to divide both sides by 64, right? When I do that, you guys, the 64 disappears, and I will be left with the velocity equals, it's going to be really close to 0.5, like 0.49. Does anybody have it? My calculator just says 0.5. So the velocity would be 0.5 meters per second. Now the astronaut, you guys, he's going a lot slower than the wrench because he's a lot bigger. So the bigger object in this explosion will end up having a smaller velocity. The smaller object in this explosion ends up having a bigger velocity.